This is the Earth's albedo in action. It is the process by which our planet bounces roughly 29% of incoming sunlight back into space. This percentage is a primary regulator of the global thermostat. If the Earth reflects less light, it absorbs more energy, directly influencing the rate of global warming. However, this reflection is far from uniform. It fluctuates depending on ice caps, the health of forests, and the thickness of the atmosphere. Because this process is so complex, understanding exactly where and how the Earth reflects light is a prerequisite for building reliable climate forecasts. We can see the scale of this complexity by looking at the equator, which divides the globe into the northern and southern hemispheres. Geographically, the two halves are nothing alike. The north has massive continents, while the south is dominated by vast oceans. Yet, satellite data shows a paradox. Despite physical differences, both hemispheres reflect the exact same amount of sunlight. They are perfectly balanced. This symmetry is a significant, unexplained feature of our planet. If such a massive planetary balance can exist without an obvious physical cause, it raises the question of what other spatial patterns our climate simulations might be missing. Searching for those missing patterns led Jianhao Zhang and a team of researchers at NOAA to look for other hidden symmetries in the way Earth reflects light. They analyzed 25 years of data from NASA's CERAS satellites, providing a constant record of solar energy bouncing off the atmosphere and surface. Their method involved digitally slicing the Earth vertically. They moved degree by degree across every line of longitude, categorizing the light sources in each section. This analysis revealed a previously unnoticed line of symmetry that splits the planet into equally reflective halves. This line runs along the 27° east and 153° west meridians, a path that cuts directly through the centers of Europe and Africa. This discovery gives us a new way to define the eastern and western hemispheres, based not on politics or history, but on the math of light reflection. Unlike the north-south balance, this new east-west symmetry appears to be driven by clear physical factors. The researchers identified what they call a triple symmetry. First, they found that these two halves contain nearly identical amounts of ice-free ocean. They also found that both sides share matching cloud patterns and nearly identical levels of light reflection from clear, cloud-free skies. This east-west balance is not a static line. It actually moves, shifting slightly from one year to the next. Those shifts are synchronized with the El Niño Southern Oscillation, the massive cycle of temperature changes in the Pacific Ocean. The connection to El Niño links this symmetry to the core mechanics of the climate, showing that it changes in rhythm with global weather patterns. With this new data in hand, the researchers used the east-west symmetry to test the accuracy of our current climate prediction technology. They checked 8 of the world's top climate models to see if they could naturally replicate this balance between the two hemispheres. The results showed that many of these advanced models are blind to this specific geographic balance. They failed to reproduce the symmetry observed by the satellites. This suggests that even our most sophisticated predictive tools have a spatial blind spot in how they handle solar energy. If a model fails to capture this 29% albedo balance correctly, its long-term forecasts of global warming may contain inaccuracies. The researchers suggest that future models must be updated to account for this east-west symmetry and its fluctuations. Pinpointing this digital blind spot allows us to refine our simulations. Incorporating these real-world symmetries will improve our climate predictions and help us see the future of our warming planet more clearly.